Moving here into section 6.3, we've been talking a lot about computing the values of trigonometric functions, looking at those as angles in the unit circle, relating to triangles, but I've almost always dealt with things in the first quadrant. So I want to look at something like, suppose I've got an angle theta like that, where the terminal point's ending up over here in the second quadrant. And how are we going to compute some things like that using what we already know about angles in the first quadrant? So the first place to start is going to be that chart we made back in chapter 5, common reference angles that really worked out easily for us. So for values of theta, we're going to be able to compute sine of theta and cosine of theta. And the reference angles that have nice values that we used before, 0, pi over 6, pi over 4, pi over 3, and pi over 2. And we had 0, 1/2, root 2 over 2, root 3 over 2, and 1. And then just the opposite for the cosine, 1, root 3 over 2, root 2 over 2, 1/2, and 0. So the question becomes, if I want to use something like this, and I wanted to calculate, say, cosine of 3 pi over 4. Right? It's not on the list. 3 pi over 4 be an angle like that. So how can we use this existing list of common reference angles to figure out how we're going to calculate the cosine of this guy? And what comes in real handy is if we remember how we defined the sine and cosine in terms of the unit circle. Remember, for a given angle, so you can put it all the way over here. Let's say theta, that entire angle. That point is cosine theta, sine theta. And it's that picture that really allows us to figure out, for the sine and cosine being related to respectively the x and y coordinates on the unit circle, what's the sine going to be? So if you think about this in terms of quadrants, quadrant 1, 2, 3, 4, if we look at an xy pair in the first quadrant, the first coordinate is positive and the second coordinate is positive. Meaning analogously that in that first quadrant the cosine is going to be positive and the sine is going to be positive. In the second quadrant, cosine is the x values are negative, y values are positive. Down here in the third quadrant, they're both negative, and out here, positive and negative. So if you relate this to what we've got here, this interpretation, cosine and sine are both positive in the first quadrant, cosine is negative and sine is positive in the second quadrant, they're both negative in the third quadrant, and the cosine is positive and the sine is negative in the fourth quadrant. So if I go back a slide to this guy, well, we had 3 pi over 4, which terminates over here in the second quadrant. The cosine of 3 pi over 4 should be the same as the cosine of pi over 4, but because we've moved over into this quadrant, where the x values are negative, the cosine values are negative, so we're left with negative square root of 2 over 2. We could look at a similar problem if I wanted to find the sine of 7 pi over 6. Well, where does that angle actually exist? Seven pi over 6 takes us all the way over there. Takes us down into the third quadrant, and so down here we know that both the x and y coordinates at this point will be negative, sine and cosine will both be negative. And we also know from our chart that sine of pi over 6 is 1/2. We should expect the same value, but with a possible change of sign. And since we're down here, both sine and cosine are negative, so I should get negative 1/2. One other thing that your authors have in this section that we should talk about, again, involving trigonometric functions. Suppose I had this triangle. Now the area of a triangle is 1/2 the base times the height. Well, here's the base. And here's the height. Well, suppose I don't know that. I don't know the height. I don't have a way to measure it. But if I've got this angle theta, I can compute this angle to be pi minus theta. They have to sum up to a straight line. So another way to think of it would be pi minus theta 180 degrees minus theta. You could do it with degrees or radians here. I'm going to stick to radians. Well, what else do I know about this height h? I'll need one other piece of data. I'll need to know one of the other sides of this triangle. I'm not going to be able to get away without that, unfortunately. So I do need to know at least two sides of the triangle. But if I've got that, I should be able to get the area. Because if I look at this triangle that I've got in red, it's got a hypotenuse A, a side h, and an angle of pi minus theta. So, using SOHCAHTOA, I'm left with sine of pi minus theta equals opposite over hypotenuse, h over a. So the height equals a pi minus theta. And so the area up here can be rewritten as 1/2 base times a times sine pi minus theta. So as an example, if I looked at, let's see, three, 10, and just to keep up with your book, we'll put this in degrees. Why not? So the area (1/2) 3 times 10 times sine of 180 minus 120. 3 times 10. That's the sine 60 degrees. 60 degrees, though, we can convert into radians. I get 1/2 3 times 10. 60 degrees in radians is pi over 3. And we know from our chart, sine of pi over 3, square root 3 over 2. And now I should be able to compute that out. So I'm going to get 30 root 3 over 4, 15 square root of 3 over 2. Now, the fact that there's a square root of 3 in here, an irrational number, tells me that if I went back up here and actually tried to measure the height of this triangle, I'd get an irrational number. I'd be taking an approximation for sure to try and calculate this. So this idea of computing the area using a sine function allows me to find that precise value. Now, in any real application, I would plug this into a computer or a calculator, round it off, depending on how much accuracy I needed for whatever application I was working on. But it's nice to be able to get this in terms of its original irrational number. You can always round off later when you actually need it. But once you've rounded, you've lost accuracy, and you're never going to get it back. So we tend to want to avoid rounding until absolutely necessary.